And then, hi everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RPCCPSIAC. It's my pleasure to introduce today's speaker, Professor Jayakrishnan Nair. He'll be speaking on equilibrium cycle, a dynamic equilibrium, and its application in ride-hailing. Professor Jayakrishnan Nair is a professor of electrical engineering at IIT Bombay. His research draws on tools from queuing theory, applied probability, game theory, and control theory to address design, resource allocation, and learning problems in networks, service systems, and smart power grids. We request the audience to keep your microphone silent for the duration of the talk, except while asking questions. Questions can be asked at any time during the talk, either by unmuting and speaking directly or by typing them in the chat box. Over to you, Professor.
Okay, thank you. Thank you very much for the introduction. The work I'm going to be presenting today has been done primarily by our soon-to-graduate PhD student, Tushar Walunj. Shiksha Singhal has also participated. She's also a former student at IIT Bombay, who's now a postdoc at last CNRS. And of course, my faculty collaborator, Veeraruna Kavitha from IIT Bombay as well. So today I'm going to be talking about a somewhat novel equilibrium concept that we have discovered in game theory, and then show a specific application of this in the context of ride-hailing platforms. So I assume that everyone in the audience is aware of the Nash equilibrium. Specifically, I'm referring here to the pure Nash equilibrium. This can be thought of as being the cornerstone of non-cooperative game theory. And if I think about the Nash equilibrium from a dynamical standpoint, in other words, if I'm thinking of game dynamics, right? For example, best response dynamics, one can think of the Nash equilibrium as basically being an equilibrium associated with that dynamical system, right? When you view it from a dynamical standpoint, we understand, of course, that in dynamical systems, dynamics by no means need to converge. And we do have several dynamical systems of interest where the dynamics tend to, in fact, oscillate indefinitely rather than converge to an equilibrium. And so the goal of this equilibrium notion that I'm going to be presenting is essentially to capture the outcome of oscillatory game dynamics. Okay, so with that kind of very high level introduction, let me mention that the talk is going to be, as I suggested, in a couple of parts. So I will spend most of my time describing this novel equilibrium notion called the equilibrium cycle. This is a set valued notion which can be thought of as a generalization of the classical pure Nash equilibrium. I will give several examples of equilibrium cycles occurring in games that are of interest in the economics community. And then finally, I will talk about an application in ride hailing, where we will study the competition between two ride hailing platforms and demonstrate an equilibrium cycle that shows up as a result of this strategic interaction. So let me begin with the first part of this talk. I'm going to start first with an example. Okay, so this is actually a classical example in the economics literature. There are several papers on this. It is called the visibility game, right? This is described as follows. So consider a non-cooperative game with two players. And for the purpose of this talk, let's pretend that the players are the blue player and the red player, right? Each player plays an action, which is a real number in the interval between 0 and 1. Right? So that's the action space for each player. And the utility functions of each player are given by this formula. Now, this formula might be somewhat cumbersome to parse. So here is an easy interpretation of this utility function, right? So imagine that the unit interval represents a stretch of highway, right? On which these two players, the red player and the blue player, these are advertisers who want to place a certain billboard, advertising whatever product it is that they want to advertise. Okay. So in that case, interpret the action of each player, AB for the blue player and AR for the red player, as the location where they choose to place their billboard along this stretch of highway. And so the interpretation here is that as cars make it through the highway, at some point they encounter the first of these two billboards, right? And the content of that billboards remains in the consciousness of the rider until the time they encounter the second billboard, right? And so suppose that the blue player, as this figure suggests, places its billboard first. then the utility of the blue player is basically the distance between the blue player's action and the red player's action, right? Once the car crosses the location where the red player has placed its billboard, then the consciousness of the rider is actually now occupied by the content of the second billboard, the low attention span people that we are, and that in turn remains the consciousness of the rider until the exit out of the highway, right? So that's the way to interpret this game. Whoever plays a lower action, in other words, they are earlier along this stretch of highway, their utility is basically the gap between their location and the next one, and whoever plays later, their utility is the gap between their position and one. Okay, that is exactly what the equation above describes. Okay, so now let us understand what kind of dynamics you might expect in a simple game of this nature, right? This is the unit interval. So suppose there is only the blue player, right? If only the blue player exists, then it would like to place its billboard at the origin, right? Because that way it gets a utility of 1, right, over the entire interval. But if the blue player is playing this game, the best response for the red player is to basically place its billboard just adjacent to the blue player to the right. Right? That way the blue player's utility comes down drastically, whereas red player gets a utility of approximately close to 1. Now, for this play of the red player, the blue player in turn has an incentive to go further right of the red player, diminishing the red player's utility to nearly nothing, and then now the blue player corners, right? And you can imagine that this thing keeps going where each of these players has an incentive to basically move to the right of the other player so that they get a bulk of the utility and the first player gets less. Okay, now this dynamics will essentially go on until you have one player, for example, sitting close to the halfway mark. When one player, for example, in this figure, the red player is close to the halfway mark, it is no longer in the benefit of the blue player to play to the right of the red player, because that way the blue player would get a utility of less than half. So therefore, at this point, the blue player has an incentive to go back all the way to the origin, right? At which point the red player has an incentive to play to the right of the blue player and so on, right? And so you can kind of see that if I think of, so this is a discontinuous game, so best response dynamics don't really exist. But if you're willing to think of better response dynamics, it seems that natural dynamics of this kind would kind of oscillate indefinitely with the actions being in the first half, the left half of the unit interval. I think there is a question. Somebody has raised their hands. Parimal, you have a question?
Yes, JK. Sorry, I missed in like initial few minutes of the talk. If you could just flash the question. The second thing which was related to that, somehow you're assuming that everybody starts from zero and ends at origin, right? But there is some merit in having billboard sort of later because people join at different times, right? I mean, at different places, but that's not what
So
you.
yeah, so do you want me to review what the game
Just
is in
you
the
put
first
the
place?
question because I missed that, so I didn't.
So this is the utility function associated with the game. So the idea is that there is a unit interval. You have two players. Each of them chooses a position on this unit interval.
Right.
Whoever chooses the earlier position, in this case, the blue player, gets a utility equal to the distance between the blue position and the red position. And whoever plays later gets a utility equal to the distance between the red action and the one. Right? So this is the utility function, right? So this can be interpreted from a timing standpoint, from a visibility standpoint, whatever. And so this is the game that I'm describing as an example. And to answer your question, so this is a picture that I have drawn purely for illustration where I've assumed that players are starting at 0. But if you spend some time thinking about this game, you'll see that no matter where people start and in what order,
It doesn't
eventually you will essentially cycle in this, 0 to half interval, right? So
matter.
yeah.
Okay. Thanks, JK.
Great. So yeah, so what I hope we can appreciate is that it looks like these dynamics seem to oscillate in the interval from 0 to half. At this point, let me also just point out that this is a well-studied game in the economics literature where people have studied the mixed Nash equilibrium. So it turns out that there is a symmetric mixed Nash equilibrium associated with this game. Interestingly, the support of that symmetric mixed Nash equilibrium is not 0 to half, but rather 0 to 1 minus 1 by e. So that's just an interesting comment about this game. Now, this might feel like a somewhat, contrived example, but it turns out that these kind of oscillatory dynamics have also been observed in real life. So here are some studies on gasoline prices.
Sir, can I ask one more question, JK? If in the
Please go ahead.
so, if you go back to the previous slide, so when you say dynamics, what do you mean by dynamic? I thought you were looking for equilibrium, right?
Yeah. So I'm thinking of, I'm not specifying what dynamics I'm referring to yet. Think of these as reasonable dynamics, like best response dynamics or epsilon best response dynamics. So
I see,
think of
because I was
those.
thinking once you put a billboard, you're not going to change it. It's something
This
which
is just for motivation. Yeah. So you can think of it as repeated plays. The billboard thing is just an example from the standpoint of a visibility interpretation. You can think of a timing interpretation of when I choose to show up for a particular, event or something of that sort, right?
and you
Similar
think that every
interpretations
time I
hold.
would do something else because
Exactly. Yeah. So there are other interpretations of this game which are more amenable to a kind of dynamics type
but in this case,
interpretation.
what would you consider dynamics? You would consider dynamics as my evolution of where I'm showing up, the timing of
Exactly. I evolve my actions over time,
oh,
presumably based on the history of what I have observed and what my opponents might be playing.
all right, thanks.
Yeah. Okay. So here is a case study of gasoline prices. I believe this is from the United States, where you can see that there are these different petrol retailers whose prices kind of oscillate as time goes on. And what you see at the bottom curve, that shows basically the wholesale price that kind of corresponds to the kind of input price or the cost price for these retailers. And you again see this kind of oscillatory behavior where one guy raises their price, that in turn causes, kind of passengers to or customers to go to a different pump. And then that in turn causes, that pump to raise their price and so on. And kind of people keep oscillating their prices, in a sort of pattern of this kind. These kind of cycles, they're also referred to as Edgeworth price cycles. These cycles have also been observed in the gasoline market of Canada, where if you account for the fact that the input price or the cost price is actually changing, and if you flatten out with respect to that, it feels like these prices are actually oscillating in a certain band, the upper end of which is the monopoly optimal price. If I was the only one, selling petrol in a certain area, what would the price be? And then there is the lower end of the band is the marginal cost, right? I'm selling with no profit margin whatsoever. It seems like the response dynamics tend to oscillate within this band over time. Yes, there's a question.
Yes, so sorry, JK, I'm asking so many questions because it's so interesting. So the thing is that you decided this utility function, but really, if you think of this gasoline market, which I like this example, is that if you raise price too much, I may not go to you, but I may go to the competitor, right? So you may lose out on revenue because you have raised the price. But is the utility function which you have showed us, is it related somehow to that question where think of there's multiple
No.
competitors in the
Don't tie
market?
these. Yeah. All
Oh,
of this is
there's
just
no.
building up to the definition of an equilibrium cycle, which I will do for a general game. So I
Right.
gave one example of a visibility game where I gave you an explicit utility function and showed you that for that game, it looks like reasonable dynamics would oscillate indefinitely in a certain interval. And these are just empirical observations that people have found, which suggests that actions tend to oscillate over time. I'm not trying to impose a utility function on this particular setting of gasoline pricing, nor am I trying to explain the specifics of this game. That's not the purpose of this talk. This is just to point out that these kind of oscillations are not just theoretical, they tend to arise in practice as well. That's all.
Okay, thanks.
So having said that, now let me set up formally what the definition of the equilibrium cycle is. So here is the non-cooperative game setup that we will consider. So we will consider a game with finitely many players, capital N of them. Each player has some action space. The script AI refers to the action space of player I. We make no assumptions on what this action space is, except to say that it is a set in some metric space. In other words, I can talk distance, right, in this action space. And finally, the utility of player I is denoted by UI. It is a function of the action profile, right? And it gives you a real number as a function of the action profile. So the script A is the combined action space. It is a Cartesian product of the action spaces of all of the n players. So this is the standard setup for a non-cooperative n-player game. And in this setting, here is the definition of the equilibrium cycle. This is the novel equilibrium notion that we are introducing. So an equilibrium cycle is basically a closed subset of the action space. So it's a closed set of the form E, which is a Cartesian product of components EI, I running from 1 through n, right? So if I consider a two-player setting, as I have shown in this picture, and if I consider that each of these EIs are essentially intervals, then the equilibrium cycle basically becomes this rectangle. So it's important to note that the equilibrium cycle is a closed set, which is a Cartesian product subset of the action space of the game. Okay. Now, such a set E is called an equilibrium cycle if it satisfies three properties. So let me first describe the first of these properties. Now, we'll parse the text of the properties in just a bit. Let me first describe the property to you pictorially, right? So suppose I consider any player I and freeze an action corresponding to the opponents of the player, right? So it's customary in game theory to represent all players other than player I by minus I. So in this case, A minus I, suppose, is the action profile associated with all the other players excluding player I, right? This action A minus I belongs to the component of the equilibrium cycle set that we are actually trying to define, right? So all the other players have played an action within their respective components of the set E. In that case, there exists an action AI corresponding to player I, which also belongs to its component of this set E, such that the following is true. This particular choice AI actually beats any action that lies outside of the set EI. That is what mathematically is being said in the text there. So for any player I and A minus I belonging to E minus I, there is some action AI in the set EI such that the utility that player I derives from playing this particular action, given the actions of all of everybody else, this utility exceeds that of any action that it might play outside of the set EI. So in words, what this means is that if all other players are playing their actions within their respective components of this set E, then player I also has a strict incentive to play an action within this set, right? So this you can think of as a statement about stability against external deviations from this product set E, right? So once again, you should think of this as a generalization of the pure Nash equilibrium, right? So the pure Nash equilibrium is not a set valued notion, but the idea is that given that everybody else plays a certain action profile, I have no incentive to deviate. This is a set valued generalization of that, saying that if everybody else plays within their respective components of this set E, I have an incentive also to play within my component of the Cartesian product E. Okay, so this is the first condition that an equilibrium cycle must satisfy. The second condition is the following. This again is a bit to parse. So let me first describe it pictorially, right? What this means is that suppose that all players play within their respective components, right? So in particular, let's say so all players play within their respective components. Then we are saying that there is at least one player I who has an incentive to deviate, but deviate to a different point within its own EC equilibrium cycle component, right? So there is at least one player I who has a strict incentive to move to a different action A hat I, which not only makes it better than where it was before, but it is also better than any outside actions outside of the component EI. This is what mathematically the second statement says, that for any action profile A, there is at least one player I that is quote unquote restless. In other words, there is at least one player I who has an incentive to deviate, but importantly to deviate to a different point within its component of the set E, right? And moreover, this deviation is of course leaves it better than it was in the original action profile, but this deviation is also better than any quote unquote outside action, right? So you see that the second property is a contrast from the first property. While the first property says something about the stability of the set E, right, with respect to external deviations, the second property tells you that there is a certain instability with respect to internal deviations. Somebody is always restless within this set. So if everybody plays within the set, you have an incentive to play within the set as well. But if everybody is playing within the set, somebody is going to be restless. At least one player will want to move to a different action unilaterally, right? So there is unrest within, so to speak. which, from a dynamic standpoint might signal, oscillatory behavior. That's the second property. And finally, the third property is minimality. So no strict subset of E satisfies the preceding two conditions, right? So an equilibrium cycle is essentially a closed Cartesian product subset of the action space, which satisfies, as I said, stability against external deviations, instability with respect to internal deviations, and minimality. Right? So this defines formally the equilibrium cycle. Okay. So having now defined the notion formally, let me revisit the visibility game that I had started this discussion with. In this case, one can prove formally that the Cartesian product of the first half of the unit interval with itself is in fact the unique equilibrium cycle associated with this game, right? So we can prove that all the three properties that I mentioned just earlier actually do apply to this particular set, 0 to half raised to 2. Okay. Let me give you, yes, I think somebody has a question.
Hi, Jayakrishnan.
Yes.
But why do you want to call it as equilibrium cycle? Because cycle, I mean, it suggests something like closed orbit in the state space or something like that, right? But here, or action space in this case, but it's not like that, no? So, for example, okay, I mean, the agents could still be restless within that set E, but maybe you could even end up with some chaotic behavior and all that, no?
Oh, absolutely. Absolutely. Yeah. So I
So,
meant, yeah. We mean
so why not
for the
just call it
cycle.
as some equilibrium set, perhaps?
Sure. Yeah. So we
Okay.
mean cycle in the sense of how, for example, limit cycles are described. But really, I agree with you. It doesn't have to be cyclical behavior because this is ultimately a static notion. What it is
Right.
meant to capture is basically the limit set or the set of all limit points associated with the dynamic.
Mm.
That is kind of
Yeah,
what
yeah,
we're
yeah,
talking
yeah,
about.
yeah, yeah. So yeah,
Thanks.
so it need not even be a limit cycle actually, right? So
It doesn't have to
under
be
the
a
best
cycle.
response dynamics, let's say.
Agreed.
Right. Okay, fine.
Right. So here is one other example that I would like to give for the equilibrium cycle. This is the Bertrand duopoly, right? So this is a very classical, game that people study in the economics literature. I'm going to describe this with two players, which you can think of as basically producers. The action space of each player is basically going to be the interval from 0 to infinity. The action specifically is going to be the price that they retail their good/service at. And there is a certain demand function, which I'm going to simplify and assume is linear, right? So at price P, the demand in the market is basically a linear function of P, such that when the price is 0, the demand is alpha, and the demand decreases without loss of generality at slope 1, such that when the price becomes alpha, the demand drops to 0. Okay. So with this demand function, here is the classical utility function associated with the Bertrand duopoly, right? So the idea is the following. The utility of player I, when it quotes a price Pi and its opponent quotes the price P minus I, is as follows, right? If player I actually quotes a lower price than its opponent, then it basically corners the entire market, right? So the entire demand will actually flow to it, and that demand is going to be the demand function evaluated at the lower price Pi, right? So the utility of player I in that case is going to be the demand times price minus marginal cost, right? So let's C denote the marginal cost of production. So whatever excess the price is from the marginal cost, that times demand, right? That is going to be in some sense the profit or utility associated with player I. If these two players actually give quote the same price, then essentially the demand that is going to be realized is going to correspond to the common price that these two players choose. And one assumes that the demand is going to be split equally between these two players. And finally, if player I actually selects the greater of the two prices, then it gets nothing, right? Because as I said, the entire market goes to the lower of the two prices, right? So this is a classical game called the Bertrand duopoly. And it is very well known that in fact, C, C is the unique pure Nash equilibrium of this game, right? So this is an equilibrium where both players are essentially operating at marginal cost. Nobody's making any money, okay? So this is well known in classical. What we consider is a small twist associated with the Bertrand duopoly, where we additionally introduce what are called operating costs. right? Which means that a player can essentially choose whether or not to even participate in the market in the first place, right? So now we will assume that the action space for each player is basically price union a certain element which we are calling N naught. So playing an action N naught basically indicates that I'm not operating at all, right? From a metric standpoint, I can just denote this N naught as a negative number, right? So think of N naught as -1 if you want. So setting price -1 in this notation indicates that I'm choosing not to operate in the market at all, okay? In this case, the utility function of works as follows. So once again, this is the utility of player I when it quotes a price pi against an opponent price of p minus I. Now suppose that player I is actually operating and is choosing the lower of the two prices, then it makes this utility. It is going to see a demand of D of pi as before. The revenue is going to be pi minus marginal cost times that demand. But in addition, there is also a cost associated with the fact that it is operating. And that fixed cost is what we are denoting by OC, which is our operating cost, right? So if you operate, you pay this positive, you pay this positive cost or negative penalty associated with the choice of actually operating in the market. On the other hand, suppose that both players actually operate and offer the same price, then same thing as before, the revenue gets split between the two because the demand gets split between the two, but each of them pays the operating cost as well. So you see the minus OC there. On the other hand, if player I operates but offers the higher of the two prices, then it gets none of the demand, it makes none of the revenue, but still incurs the operating cost, in which case its utility is in fact minus OC. And finally, of course, if it chooses not to operate, it gets a utility of 0. Okay, so this is a, so this is a generalization of the classical Bertrand duopoly. In the classical version, remember that there is a unique pure Nash equilibrium. In this case, what we can prove that if a certain condition is satisfied, which I will interpret in just a bit, this game actually admits a unique symmetric equilibrium cycle. So the expression for the intervals associated with this equilibrium cycle are a bit ugly, so I'm not going to actually write the expressions down. But let me highlight what the condition here is. The condition that alpha is greater than C plus 2 times square root OC is the condition that if a single player was operating alone, right, in a monopoly setting, there is a positive net utility to be had, right? Clearly, that positive net utility can only be had if the operating cost is small enough, right? So this is exactly that condition. So long as a monopolistic player has some incentive of playing this game, so to speak, of operating in this market, in the presence of this operating cost, the game does not have a pure Nash equilibrium, but instead has a symmetric equilibrium cycle. Okay, so we've seen that there is a small, not unnatural generalization that we can apply on the Bertrand duopoly, and the nature of the equilibrium changes drastically. Next, I would like to talk about connections between the equilibrium cycle.
Just one question, JK, in the previous.
Yes.
But what will that equilibrium be? Will it be like before you said in Bertrand duopoly, right? You working at almost marginal cost, right? At CC, what would that be? Be non-trivial, like you'll actually make money?
No. So yes, short answer is yes. Actually the behavior is very similar to the petroleum example that I had stated. So you will see that the band really corresponds to the upper end of the band corresponds to the monopolistic pricing, and the lower end of the band essentially corresponds to the point where, if you operate at a price below this, then your utility starts becoming negative, right? So you basically oscillate in that band. That's the support of your equilibrium cycle. So the intuition is again clear, right? So in the absence of any other player, I'm going to operate at monopoly pricing. You come along and you undercut me, right? And then I undercut you. And this keeps going on till the point where it is no longer feasible for one of us to undercut the other. And so therefore, I just choose to exit the market entirely. At which point you now have an incentive to go back to the monopoly pricing, right? So that's kind of the intuition for why it holds. We prove formally that that's an equilibrium cycle.
Thanks, Jake.
Okay. So now I'm going to make, so this is, as I said, this is a novel equilibrium notion. As such, there's nothing dynamic about the equilibrium notion. This is a static notion with some dynamic connotations, right? That's the goal. I want to make connections between this and other related equilibrium notions that people have studied in the past. right? So the first connection we will make is to this notion of curb sets that were defined by Basu and Vaibul back in 91. So a curb set is also a Cartesian product subset of the action space A that contains its best responses. Right? So the idea is that you pick any element of A and consider any player and say, what is your best unilateral deviation? That new action profile that the unilateral deviation corresponds to must also lie in the same set. Right? So the set is closed with respect to best responses. Such a set is called a curb set. So let me illustrate that via this simple two-player game. So I have a vertical player and a horizontal player. The vertical player essentially plays left, center, right. The horizontal player says, okay, up, middle, down. And you can see that the utilities have been contrived in such a way that essentially there are two curb sets in this setting, right? One of the curb sets correspond to the orange region, right? Where you can see that in that region, picks any one action profile and the best response of any one player to that action profile also lies within that same set, right? So that's one curb set. And then of course, there is a corner singleton subset of the action space, which corresponds to the action D, R, which is in fact also a pure Nash equilibrium and therefore also a curb set, right? So this is a simple two-player game where in fact there are two disjoint curb sets, right, as defined by Basu and Weibel. They also define this notion of a minimal curb set, right, analogous to how we do. A minimal curb set, as the name suggests, is a curb set, no strict subset of which is also a curb set, right? This minimality is useful because otherwise the entire action space is obviously a curb set, right? So this minimality is what makes the definition meaningful. You can see back to the example that I have below that both of the curb sets in this are in fact minimal. You take any one of these curb sets, no strict subset of that is a curb set in that it is closed with respect to best responses, right? And finally, there is a small tweak that we add to minimal curb sets, and we say that a non-trivial minimal curb set is one that does not contain a pure Nash equilibrium, right? So of the two curb sets in this example, the green one is not non-trivial because in fact it contains a pure Nash equilibrium. Only the orange one is in fact non-trivial, right? So that notion of a minimal curb set for games where best responses exist is classical, has been around for a long time. We are only adding one qualifier saying that a non-trivial minimal curb set is one that does not contain a pure Nash equilibrium. Okay. So with this, what we are able to prove is that in fact, non-trivial minimal curb sets are equivalent to equilibrium cycles. Okay. So it's important to note that this equivalence is only for the class of games for which the curb set is well defined. In other words, for games where best responses exist. These are also sometimes referred to as best response games. So in best response games, equilibrium cycles are equivalent to non-trivial minimal curb sets. However, equilibrium cycles are also well defined in discontinuous games, several examples of which we have seen so far. So in those games, best responses do not exist. And so it is meaningless to talk about curb sets, right? So you can think of the equilibrium cycle as generalizing the notion of curb sets due to Basu and Weibel. But we are generalizing this beyond best response games. In particular, we also allow for discontinuous games, right? Games where the utility functions are discontinuous with respect to the action profile. This is one connection I would like to make. If I further specialize even beyond best response game down to finite games, then again, there is more that can be said. When I say finite game here, I mean finite in the sense of the action space, right? The collection of actions available to each player is
One
finite.
question here, JK, in the previous
Yes.
slide. So maybe my understanding of best response is not correct. I thought the best response was always the given other player's action, what is the best action I should take?
Yes.
Continue or discontinue doesn't change anything for me, right? So, but you said something about discontinue.
Okay, hang on. Yeah, let me clarify. So the best response games are those where best responses exist. Okay. Now, if your game has finitely many actions, then we know that a best response always exists. Suppose you and I are playing the game, given your action, fixing your action, there is obviously an optimal response for me, and that becomes my best response, right? So best responses are guaranteed to exist in games with finite action spaces.
Right.
If your action spaces are continuous, then a sufficient condition for the existence of best response is that the utility functions are continuous. If my utility function is a continuous function of the actions, then from continuity, I know that whatever you play, there exists a certain maximizing action response from my side. And so best responses are guaranteed.
But to me, why can you not generalize this to finitely many discontinuities? Because I would look at, suppose I have 3 discontinuous intervals, right? And in each of them, I can find the best response and I can pick the best of these 3 in 3 discontinuous, intervals. Is it not?
If you go back to the examples that we have seen, including the visibility game, you cannot undo the discontinuity is in the action space, remember, right? So because when basically there is a wild swing in my utility, whether I price myself slightly above you or slightly below you, all of the games you have seen so far have that kind of flavor. So there is no way of there's no way of defining best response in that case.
Okay.
Can I comment on that?
Yeah, please.
Is it due to the existence of supremum but not maximum? Is that the reason?
Yeah. So
I
that is,
think that is the reason. No?
But yeah, there's no maximizing, there's no optimal response.
Yeah.
Right. So in discontinuous games of those kinds, best responses do not exist. All the examples we have done so far, except for the finite example that I made for curve sets, those are discontinuous games. And so best responses just don't exist for those games. But the notion of equilibrium cycle that we have done via those 3 requirements, that makes no stipulation about the existence of best responses. So that's a notion that can be defined even beyond the set of games for which curve sets are well defined. That's the point. So let me specialize further to finite games. Here again, as I said, by finite, I mean that the action space of each player is finite. We have always been working with finitely many players, right? For this, you can actually define what is called the best response graph. Okay, what is the best response graph? The nodes of this graph correspond to action profiles, vectors corresponding to the actions of each of these players. And I will have a directed edge from one action profile, say AI, comma A minus I, to A hat I, comma A minus I, if A hat I is in fact the best response of player I against A minus I, right? So the edges, the directed edges associated with the best response graph exactly correspond to best responses of some player or the other, right? So you can see that these edges are only between action profiles that differ in exactly one component, and the edge exists if that player not only has a unilateral deviation to make that particular change, but in fact, if that is the best response given the actions fall of the other players, right? So just to kind of get everybody on the same page, note that from the best response graph, any sync node, a node from which there are no outgoing edges, is clearly a pure Nash equilibrium. That much is clear. And moreover, note that if you look at dynamics in finite games as random walks on this graph, then a random walk on the best response graph will necessarily end up in a strongly connected component, which is a sync component, right? What does strongly connected component means? A strongly connected subgraph of my best response graph is basically a collection of nodes which are all strongly connected. Everybody is connected to everybody. And sync in the sense that there are no outgoing edges from this component to anybody else, right? So it can be, this is a classical result, of course, that random walks will end up in a strongly connected sync component, something we will also refer to as a sync SCC. Okay, so now comes the connection to equilibrium cycles. So what we prove is that in this context of finite games, any equilibrium cycle is necessarily a sync SCC of the best response graph, right? But the converse is not necessarily true. To prove something in the opposite direction, what we can show is that a rectangular, when I mean rectangular, I mean a Cartesian product, right? A rectangular non-singleton sync SCC of the best response graph is an equilibrium cycle, right? So this dichotomy between equilibrium cycles and sync strongly connected components comes from the fact that fundamentally we have defined the equilibrium cycle as being a rectangular object, right? It's a Cartesian product of subsets of the action spaces of all of the different players. Whereas fundamentally, there is no reason for any sync SCC of a best response graph to have that Cartesian product structure, right? So equilibrium cycles are organically sync SCCs, but sync SCCs If they are rectangular and non-singleton, then they become equilibrium cycles, right? You can come up with a suitable generalization of equilibrium cycles that does not have this rectangularity requirement. But it turns out that for continuous games, that rectangularity requirement is crucial for us to be able to prove minimality, right? So that is the reason why we defined the equilibrium cycle as a rectangular object, but then the connection to sync SCCs, has some subtleties involved. So that in fact brings me to a conclusion of my discussion, my broad discussion of equilibrium cycle. You can think of this as just a moment, Pawan, you can think of it as a set valued equilibrium cycle, which kind of generalizes the notion of a pure Nash equilibrium, which seeks to capture the outcome of oscillatory game dynamics, right? I'm saying that without specifying what dynamics itself I'm referring to. It's a static equilibrium notion, right? And what does it seek to capture? It seeks to capture the limit set associated with these dynamics. To be even more precise, it seeks to capture, for each player, you look at the limit set, it seeks to capture the Cartesian product of those limit sets. That is what more formally the equilibrium cycle seeks to capture. The key feature is that the definition does not require continuity or existence of best responses. So specifically, it is also applicable to discontinuous games where best responses need not exist. There are three defining properties. You have stability against outside deviations, instability against internal deviations, so unrest, and then finally minimality, right? And we talked about how it generalizes the notion of minimal curve sets to beyond best response games. And it is also connected to strongly connected sync components of the best response game, of the best response graph in the context of finite games. Yes, Pawan, you have a question.
So in finite games, do you still need the action space to be a subset of the metric space? Yeah.
No.
You don't require it, right? So,
Yeah.
so if you relax that, then do you still require that rectangular condition? I think on your previous slide, right? So you wanted.
So the rectangularity condition and the closedness, right? We said that it has to be a closed set. These things come from having to give a generic definition of the equilibrium cycle, which applies both to finite as well as continuous games. If I wanted to write a separate notion which is specific to finite games, one can do it without this rectangularity requirement. And of course, when it comes to finite games, topological considerations of closeness and so on don't really apply.
Yeah. Okay.
Great. Okay, so this concludes my general discussion about the equilibrium cycle. Let me just check the time. Okay, so let me now quickly run through my example, which comes from ride hailing. So this is, we are going to be making a shift away from the general equilibrium notion to a very specific game in the context of competing ride-hailing platforms, which roughly speaking fall within this larger class of applications where one is dealing with matching platforms, right? You're trying to match, for example, customers to service providers of various kinds. Right. So specifically, I'm talking about ride-hailing platforms. There is a considerable literature already on ride-hailing platforms describing, addressing questions involving modeling, performance evaluation, how should fleets be sized, what is optimal pricing, optimal routing, optimal fleet placement, and these questions have been studied extensively. The specific question we are going to be looking at is, what is the impact of competition between ride-hailing platforms, between Ola and Uber, if you will. So here is a simple stylized model with which we will analyze this problem. So we have two competing ride-hailing platforms. I'm going to call them platform 1 and platform 2. And the way we model this is that passengers, right, come into this system as per a Poisson process with an aggregate rate of lambda, capital lambda, right? And in a manner that I will describe in a bit, this overall Poisson arrival rate of passengers is actually going to be split between these two platforms into two Poisson streams with a rate of lambda I. So lambda I is the Poisson arrival rate of ride-hailing requests as arriving on platform I. Okay. I will tell you how this split of the total arrival rate into these two lambda 1, lambda 2 streams is going to be modeled subsequently. And so I'll tell you how this split is defined based on quality of service considerations. And so what we will do first is model each of these platforms given that split as a separate BCMP queuing network. Right? I will describe that queuing network in just a bit. And then having described that queuing network, I'll be able to describe to you how, based on quality of service considerations, the split of the arrival rate between the two platforms is actually realized. Okay, so here is the BCMP model for platform I. So imagine that from the outside world, drivers are actually entering this system at a Poisson arrival rate of eta I. Okay, passengers, as I told you, are arriving at a rate lambda I. Now, when a passenger comes in, if there is a driver available in the driver queue, then of course, in addition to this, the platform also sets a certain price. Let's call that phi I. Okay, it can depend in general on the number of waiting drivers at that point of time. So when a passenger comes in, with some probability, the passenger accepts the ride on the first available taxi, and then the ride gets initiated. The probability with which the passenger accepts the price is basically indicated by this function f of phi I, which captures the price sensitivity. Right? So SF is a function where that function of phi I represents the probability that the price phi I is going to be acceptable to the incoming customer. Okay. If the customer does not find this price acceptable, the customer simply leaves. Now, once the ride commences, we assume that the duration of the ride is exponentially distributed with a certain parameter, which we are calling mu I, at the end of which the driver will rejoin this queue with a certain probability, let's call it Pi, and with probability 1 minus Pi, the driver leaves, right? So you have drivers coming in from the outside world and drivers also exiting the system, right, at a certain rate. Now, so the aggregate rate of arrival into this driver queue is going to be in fact composed of not just this eta I exogenous arrivals, but also the drivers who are rejoining after rides. In addition, we will assume that these drivers are also impatient, right? While they are waiting for a ride, it's possible for them to abandon the queue. They abandon independently at a rate beta I. And the assumption that we will make essentially to model this as a BCMP network is the following, that when they do abandon, they again enter this kind of exponential, dummy ride, if you will, at the end of which, with probability Pi, they rejoin the queue, and with probability 1 minus Pi, they leave, right? So this think time when they actually abandon the queue can either be interpreted as them taking a break, going home for lunch, or you can imagine that they've taken up some local ride, which also takes the same amount of time, distribution wise, at the end of which they either rejoin this queue, making themselves available, or leave for good, right? So this is the BCMP network. Specifically, the parameter beta I represents driver impatience. A higher value of beta I indicates a higher level of driver impatience, right? Higher rate of abandonment from the driver queue. Right? So the aggregate arrival rate into this driver queue is going to be denoted by EI, which is composed both of the exogenous arrivals, but also the returning drivers. So this can be cast, it turns out, as a BCMP network with two stations. The details are not very important right now. Specifically, this allows for a product form stationary distribution, and this formulation is quite general. It allows for multiple zones, even though for simplicity, we'll consider just one. As I mentioned before, it allows for dynamic state-dependent pricing and so on. So this is, from an analytical standpoint, a fairly powerful model to work with. Right? So having now modeled each of these platforms as a BCMP network, how are we going to define the split of the arrival rates? The split will be done by modeling as a Wardrop equilibrium, right? So this is going to be a Wardrop equilibrium with respect to the overall blocking probability, right? What is the overall probability that an arriving customer into platform I is going to leave without actually getting a ride? This blocking can happen two ways. Either there was no driver available itself, in which case the passenger left, or there was a driver available, but the price was too prohibitive, so I left. Right? So this Wardrop equilibrium basically indicates that we are modeling the arrival rate as being split in a manner that the overall blocking probability is equalized between platforms 1 and 2. Right? So that is the meaning of this Wardrop market share split. So with this model, now we have a non-cooperative game between these two platforms. The action is the pricing policy, right? How do I price my rides? The payoff is going to be, or the utility function is going to be the rate at which the platform derives revenue. So what are they competing for really? They are competing for market share, right? Which in turn is dictated by their pricing. To simplify, to make this game tractable, we will make several simplifying assumptions. Firstly, symmetric platforms. So the driver arrival rates and so on are symmetric. Static pricing, which means the pricing is not state dependent. So the action space becomes just a scalar, right? Just a one-dimensional price, a single static price that I apply on my platform. And finally, even then, we will consider a limit system where the driver impatience parameter is actually tending to 0. So we will consider the pointwise limit of the payoff functions as this parameter of driver impatience goes down to 0. So you can think of this as a regime where drivers are very, very patient. And so they stick in the queue for very long periods of time. Okay, so let me describe now what happens in this game. Let me first, for reference, consider the monopoly setting, right? This corresponds to a setting where irrespective of the pricing of the other guy, I get half the market share. You can think of that as monopoly in the sense that my pricing does not influence the amount of market share that I attract. In that case, optimal pricing is just an optimization problem. And so we can actually describe the optimal price as a function of this parameter, what we call E by lambda. What is E? E is the aggregate arrival rate of drivers into the driver queue, and capital lambda is the aggregate arrival rate of passengers, right? So this E by lambda is some sort of driver passenger load ratio. A large value of E by lambda indicates that drivers are abundant relative to passengers, and a low value indicates that passengers are abundant relative to drivers, right? So you see that the optimal price basically has these two bands. When the driver passenger load ratio is low, right? In other words, drivers are scarce relative to passengers. It turns out that the optimal price is just the price sensitivity function inverse evaluated at 2E by lambda, right? On the other hand, when drivers are plentiful, right, and passengers are what are scarce, there is in fact a fixed price, which is actually just the maximizer of phi times F5, which is optimal. Right? So you see these two bands in which the optimal pricing operates in the monopoly setting. And if you think of it from the revenue standpoint, you see that when in fact the driver load is low, in other words, drivers are scarce, then the revenue rate increases as the rate of availability of drivers increases. But after a certain point, once you have enough number of drivers, you are essentially constrained by the availability of passengers, at which point you can't really increase price anymore. So the revenue becomes flat. Right? So this is just a simple observation of this is the baseline against which we will actually compare the case of competition between the platforms. Right? So again, there are these two regimes. The left regime is where the system is over provisioned with respect to passengers. The right is where we are under provisioned with respect to passengers. I have more drivers than passengers. Okay. Now let's talk competition. Now it turns
Professor,
out. Yes.
There has been a question in the chat box. So
please.
Yeah. So the question is, are the drivers allowed to rejoin either platform after a trip?
No, for this model, we will assume that drivers are dedicated to a particular platform. They either leave for good or come back to their respective platform. The drivers don't hop around. Yeah. So I hope that answers the question. So when you have competition, this is what the equilibrium price phi star now corresponds to, which I'm showing with the red curve, right? So what we find is that when this driver passenger ratio is small, in other words, the system is over provisioned with respect to passengers, then it turns out that there is this small band in which the Nash equilibrium is in fact the same as the monopoly pricing. So the fact that there is competition doesn't matter. There's too many passengers, so I don't really basically each platform can simply operate at monopoly pricing. However, beyond that threshold, right, as the drivers become more abundant or equivalently the passengers become more scarce, now competition starts playing a role. I have to compete for the fewer passengers that there are, which causes me to undercut my competitor, in turn resulting in a Nash equilibrium pricing, which is in fact lower than the monopoly pricing. Okay, you can actually see this from a revenue standpoint as well. To the left of the first threshold I mentioned, where passengers are aplenty, the monopoly revenue agrees with the competition revenue. So you can think of this as a price of anarchy equals 1 type setting. But to the right of this threshold, you find that in fact the competition revenue, because of competition, right, the equilibrium revenue of each of these platforms is going to be less than the monopoly revenue. right? But this all happens until a certain threshold of this driver-passenger ratio. What happens beyond this point is the interesting question, right? This, in fact, corresponds to a case where the drivers are actually plentiful. In other words, the passengers are scarce, right? You're struggling to find customers, right? In that setting, we can, in fact, prove that there is no Nash equilibrium, firstly. And as you might expect, given the context of this talk, what we prove is, in fact, that there is instead an equilibrium cycle, right? So we are able to show that beyond that threshold, all the way up to a price where after that point, operating in the market is not meaningful anymore. In fact, there is an equilibrium cycle between, the two players, and the support of the interval corresponding to that equilibrium cycle is what I'm indicating with the kind of in the shaded region on the left, right? So this is what we are able to show in the context of competition between ride-hailing platforms. A natural question that comes about is that if you have an equilibrium cycle, how should I think of, in fact, the payoff between the players in that regime? This is just a kind of side comment. One easy way of thinking about payoff in the, when you have an equilibrium cycle is via this classical notion of security value. So the security value corresponding to an equilibrium cycle for a particular player is essentially its max min payoff. This M in this case is actually utility. It's a typo. It should have been U. So this is basically, I'm maximizing with respect to my action the minimum utility that I get across all of my opponent's actions, right? So this is like a robust but pessimistic, utility value, which can be applied and computed for the equilibrium cycle. And interestingly, we find that in the region where you have these equilibrium cycles, the security value of each player can basically be realized if one player plays one end of the equilibrium cycle and the other player plays the other, right? So when they oscillate in this interval, if one of them plays the minimum and the other plays the maximum, both of them get, in fact, the same utility, which is given by the security value. Again, not related to the general, theory of equilibrium cycles. This is specific to this ride-hailing competition game that we have analyzed. Right. So in that case, we can actually complete this picture and show that, in fact, there is a utility that continues to dip as passengers become scarce. Right. And again, you see that because of competition, that forces the platforms to operate at a lower and lower price, therefore derive lower and lower revenue. Right. So this is my quick application. So what we have done is analyzed a specific non-cooperative game that captures competition between ride-hailing platforms. The competition is via pricing. What we find is that when passengers are abundant, right, then competition doesn't have an impact. Each party can basically operate at monopolistic pricing. As passengers become more and more scarce, platforms have to compete for them by lowering prices. And there is a certain region of increased scarcity of passengers, of system parameters, where, in fact, not only is there no Nash equilibrium, but instead we are able to demonstrate an equilibrium cycle, right? Which indicates from a dynamical standpoint that these prices would tend to oscillate over time within a certain band. With that, I will stop, and I'm happy to take any questions that remain.
Thank you, Professor, for accepting our request and delivering such an interesting talk. I request the audience to ask your questions, if any.
I mean, amazing talk, JK. I think I'll just talk to you separately because these are more not talks but thoughts I got from your talk. We can discuss it offline.
Thanks.
Thanks.
Okay, since there are no more questions, I would like to end the meeting. Thanks again, Professor. Thank you, everyone, for attending.
Thank you. Thank you so much.